How fast a reaction happens depends on three things. And so far, the only thing we've talked about is concentration. So the amount of stuff, unless it's zero order, then if something's zero order, then its concentration does not actually affect the rate. But there are two other things that affect rate, how fast a reaction happens, and they are temperature and molecular orientation. Now, temperature is easy. In general, as the temperature increases, the rate of the reaction increases, which means the rate constant would change for that reaction as well. So rate constants are only good at whatever temperature you measured them at. We're going to talk about molecular orientation here when we get to catalysts. So let's focus on temperature. To understand how temperature and molecular orientation really affect a reaction, you have to understand how we believe reactions occur. And we believe reactions occur based on collision theory. So in order for two things to react, in order for bonds to break and new ones to form, we believe particles have to collide. Okay, and it makes a whole lot of sense that by increasing the temperature, you could increase the rate of reactions happening because if you increase the temperature, the particles are going to have more energy, and if they have more energy, they're going to collide with more force, right? Okay, and you got a greater likelihood of the reaction that you want happening to happen. Um, the minimum amount of energy needed for a collision to be a fruitful or a collision that happens is called the activation energy. Um, Without that, and this is hard to understand at first, I think, but what you have to understand is that most collisions do not result in a reaction. Most of the time, when particles collide in a solution or in the gas phase, most of the time when particles collide, they do not have enough energy to break the bonds needed or make the new bonds that form. They don't have enough energy to overcome this activation energy barrier. So what you have to understand is most of the time when particles collide, they don't have enough energy to react and they just bounce off each other. Okay. And you can see with temperature, now, if I increase the temperature, I increase the speed of the particles, and now they're going to collide with more kinetic energy. And now, if I have more energy, I get a greater chance of having enough energy to break the bonds I needed and make the new ones that I needed to make. You should have hopefully seen energy coordinate diagrams before. If not, we'll do a quick review. So this is an energy coordinate diagram. On the left side, this is where the energy of the reactants are. So this is energy of the reactants. On the right side, this is the energy of the products. And the minimum amount of energy needed for the reaction to occur is going to be the energy at the highest point on this reaction coordinate, right? It's like the summit of the mountain. And that's called the activation energy, or that's called it's called the transition state. And sometimes it's called the activated complex. So that's the highest energy point on a graph. So if you have enough energy to get to that highest energy point, then you were able to do it. Now, how much energy does it take to get from the reactants to the highest energy point, the transition state or activated complex? Well, that is the activation energy. So the amount of energy, the difference in energy between the energy of the reactants and the energy at the highest point, that is called the activation energy. And sometimes that's abbreviated E sub A for energy of activation. So that is our activation energy. Now, these energy coordinate diagrams can take two basic shapes. This is the shape for an exothermic reaction, okay? How do I know this is an exothermic reaction? Well, my products have less energy than my reactants. Since energy is conserved, then energy's got to go somewhere. It must be leaving the reaction, so heat must be exiting. The amount of energy that it leaves, that's the difference in it, or if it's endothermic, the amount of energy that gets absorbed. The change in energy is really the difference in energy between the energy of your reactants and the energy of your products. So a lot of times this is called the change in enthalpy, and enthalpy is abbreviated with a H. So this is the change in enthalpy. This is always found by taking the energy of the products and subtracting the energy of the reactants. Okay, so energy of products minus energy of reactants. So if I take the products, which are lower in energy than my reactants, I'll get a negative answer for this. And a negative energy just means it's being released. So that's how you can determine this is an exothermic reaction. The opposite shape for an energy coordinate diagram would be like this. So I'll show you what an endothermic reaction coordinate diagram would look like. An endothermic reaction coordinate diagram would look like that, where here's the energy of my reactants, there's the energy of my products, here's my transition state, here's my activation energy barrier, right? Okay, but you can see the products are higher in energy than the reactants. So if I subtract product energy minus reactant energy, this change in enthalpy, here, this would be a positive value because my products have more energy than my reactants. If my products have more energy than my reactants, that energy had to come from somewhere. It must have entered the system. So that's how you know this is an endothermic reaction. It's endothermic. Now, another thing. So we have another symbol for the transition state or activated complex. Sometimes we use a double dagger to represent that activated complex or transition. Don't ask me. Why does everything have three names? I don't know. But the activation energy barrier is the difference in energy from the reactants to that transition state or activated complex. And sometimes, yeah, we call that a double dagger for some reason. All right. So that transition state, let's talk about that double dagger or that activated complex. What does it look like? What when we get there, why do we need to get there? Like why is the activation energy depend on getting there? The transition state is usually when if you're colliding, remember we think it's collision theory, when two reactants are colliding, the transition state is usually when the two molecules are the most mangled up they're ever going to be. Okay. You think about it, the transition state highest energy point, it's when the molecules are, the most mangled up. Because if you think about it, the electron cloud from this molecule and the electron cloud from this molecule, they don't like each other. And yet they need to collide, right? Because they're both negative. So they don't want to interact. So they've got to slam into they need to slam into each other with enough energy to overcome this repulsion between their electron clouds. Now their electron clouds get mangled up, and that's going to be the highest energy state. And if they can get mangled up enough at that point, then the bond breaks, and now it all goes downhill where we make new bonds and things become more stable. So that's usually, like, if you're trying to think, what does the transition state look like? It's when it's all mangled up, right? It's when it's the most mangled up. We are, in a moment, going to learn how to solve for that activation energy barrier. So the activation energy barrier is really, really, really important, right? And I'll pop out here to the table. On an energy coordinate diagram, the activation energy is really the most important thing. Okay, let me show you why. Generally, as a chemist, we are interested in making reactions happen. And the activation energy tells you the minimum amount of energy needed to make that reaction happen. So if I have an exothermic reaction, for example, my activation energy is here. And if you think about it, my reactants are starting with this much energy. My activation energy tells me how much energy do I need to put in to make this reaction happen. And that's really important because that's up to the chemist to do, right? Do I need to heat this reaction up really hot, or is room temp giving enough energy to make this happen? What do we need to do here to make it happen? It's important to understand that even exothermic reactions that end up releasing energy, they still require energy to happen. They still have an activation energy barrier that's needed. Okay, so here's how that's possible. I like to think of exothermic reactions like a good investment, right? So this is where, like, you have to put in $50, but then you sell the shares of that stock for 100. Well, you didn't make $100. You only made $50, right? Because you had to put in 50, you got your 50 back, and then you made 50. So that's why if people struggle to understand that, the exothermic reactions, wait a minute, I thought they released energy. What do you mean you got to put in energy? Well, they release more energy than you put in, but you still had to put some in. So it's a net profit to the environment, okay? But some energy still did need to go in from the environment. You just get more energy out than you put in originally. In an endothermic reaction, here it's like a bad investment, right? You've got to put in energy. Maybe you got to put in 50 kilojoules of energy again, but then you only get like 20 kilojoules back. So you lost $30, right? Um, it's just it's every even endo and even exothermic reactions have this activation energy barrier, and we're gonna we're gonna talk about how to calculate that activation energy barrier. In fact, let's do that now. We'll come back to collision stuff. So let's jump ahead to how do we get that activation energy. We're gonna skip this molecular orientation. We'll go right to Arrhenius equation. So a guy by the name of Svante Arrhenius, who is pretty awesome. He is man, at the time he was alive, I think he understood everything that there was that you could possibly understand about chemistry. He really just did so in so many different areas of chemistry. He had such an impact. And here with activation energy, he figures this stuff out. I would not write down anything that's on the slide, except we need to talk about the fact that because we're gonna rearrange the Arrhenius equation. Essentially, the Arrhenius equation says the rate constant K is equal to some frequency factor, some constant, and then times E to the negative activation energy over RT. And we're going to rearrange this for activation energy in a more user-friendly form, like slope-intercept form. But it's important to understand that it's got the universal gas constant R in here, but we're not doing pressure volume work here. We're doing like joules work. So that R is not the 0.08206 atmospheres times the usual moles times Kelvin. It's the 8.314 joule per mole times Kelvin. So you're going to write that number down. That number should go on your formula sheet. You're going to need that. It's the energy, the joule form of R. Here is the that Arrhenius equation on the last slide, which you really have no use for. Here is that equation rearranged into slope-intercept form. So essentially what was done is they just took the natural log of both sides. Okay, and if you take the natural log of both sides, you end up with an equation that is in slope-intercept form. So this one is important. And this tells us how to make an Arrhenius plot. So I would totally write this equation down. What this equation says, again, because it's in y equals mx plus b form, is it says if we make a graph of the natural log of rate constants, versus 1 divided by the temperature that the reactions were run at. And that temperature needs to be in Kelvin, by the way, okay, because R is in Kelvin, so the temperatures have to be in Kelvin. Then what you will get is you should get a linear relationship between the natural log of the rate constants and the inverse of the temperatures they were run at. And the y-intercept should be the natural log of that frequency factor constant. And the slope here should be negative activation energy divided by R. So what we could do is if we multiply the slope by negative 8.314 joules per mole times Kelvin, we should be able to get our activation energy. Okay, so that's the handy thing. This is called an Arrhenius plot. Okay, when you take the natural log of K versus 1 over the temperatures in Kelvin, you get an Arrhenius plot, and the slope of that line is negative EA over R. Cool. So here we have an Arrhenius plot that someone has made. I didn't make this. This is an Arrhenius plot that's attempting to get the activation energy for the decomposition of ozone. So you've maybe heard of ozone. Ozone is O3. It's an elemental form of oxygen. It's pretty rare, except for in upper layers of the atmosphere. In upper layers of the atmosphere, we have a whole bunch of ozone up there because all ultraviolet light. And this is good because it reflects a lot of energy from the sun, specifically UV rays. Um, and I don't know if you guys know this or not, but in the 80s and 90s, we were just chewing up that ozone layer like it was nothing, man. In all these aerosols, we had CFCs, chlorofluorocarbons, and they would you'd spray hairspray, and they would just go super light, it would go up into the atmospheres and would just chew up ozone. And we had these giant holes in the ozone layer, and boy, that wasn't good because now you're going to let more light through, and it's going to, you're going to get more UV light, you're going to get more sunburn, and you're going to, increase your chances of melanoma. And also, it's going to impact global warming even more, right? It's not a greenhouse gas effect, but it's letting more light through, so that's not good. This is like the one success story we have, right? We stopped putting CFCs in aerosols, I think, in the 90s. And since then, the ozone layer has almost completely regrown. So we have almost completely, it has like healed itself, and we did it, right? So this is like the one thing we give ourselves a pat on the back. We have really sucked at doing a lot of other things, but boy, we did keep that hole in the ozone layer from growing too big. That was like, good job us. We did it, right? We need a win. Anyway, here's what happened. Okay, somebody ran this decomposition of ozone reaction at a bunch of different temperatures. Now, that's pretty hot. These are in Kelvin, but subtract 273. I mean, you're at like 300 some degrees Celsius here. This is hot, hot gas, hot gas. So they ran it at 600 Kelvin, and the reaction had a rate constant of 3.37 times 10 to the third, so 3,370. Then they increased it to 700. Now look what's happening to the rate constant. It's going up. Okay. As temperature increases, the rate's going to increase, which means the rate constant is going to increase. So look at what's happening. Each time we increase the temperature, the rate constant increases. And then what somebody did is they took this data and they said, okay, where's my pen? There it is. They said, okay, let's take the natural log of these rate constants and the inverse of these temperatures, so 1 divided by 600 and the natural log of 3,370, and let's plot all these values. So, and literally, they probably just put it in Excel and made Excel do all the work for them. But this is an Arrhenius plot, okay? And what I want to do is I want to take this information, I want to take the line of best fit for this Arrhenius plot, and I'm going to use this to get the activation energy for the decomposition of ozone. So can we take this graph and that equation of best fit from the graph, and can we use it to get the activation energy for this reaction? Give me a second to write this on the board. So I want to get the activation energy for this graph. Now here's the cool thing. Okay, this is what you're essentially going to be doing tomorrow in the lab. Tomorrow in the lab, you're going to run a reaction at 4 different temperatures and find how fast they happen, the rate. And then what we can do is we'll take the natural log of the rate constant versus 1 over the temperature, okay, and we'll make an Arrhenius plot. And from that Arrhenius plot, we'll be able to solve for the activation energy. How are we going to do that? Well, the Arrhenius equation says the natural log of the rate constant is equal to negative EA over R times 1 over the temperature plus the natural log of the frequency factor. So what we can do, the first thing to get the activation energy, the first thing we can do is we can say that slope, okay, that slope, negative 1.12 times 10 to the fourth, is equal to negative EA over R. Now, what is R? R is 8.314 joules per mole times Kelvin. Now, the Kelvin cancels out when you multiply it by the 1 over the temperature. So the Kelvin goes away. So we're really left with joules per mole. So now, if I multiply both sides by negative 8.314 joules per mole, We get a big old number. We get 93,100. I'm going to round it to 3 sig figs joules per mole equals my activation energy barrier. Now, activation energies are usually reported in kilojoules. So we need to divide that by 1,000. That's going to be 93.1 kilojoules per mole. That's my activation energy barrier. So if I was going to draw the reaction coordinate diagram, whatever the energy of my reactants are, that activation energy barrier is 93.1 kilojoules. Okay, it would be 93.1 kilojoules of energy that needs to be put in to get to the transition state. Now, I don't know if that reaction is endo or exothermic. Let's say it's exothermic. You just got the activation energy barrier, 93.1 kilojoules. So by making a plot, an Arrhenius plot, and then by finding the slope from the line of best fit, you can get the activation energy simply by multiplying by negative 8.314, and that'll get you the activation energy there, 93.1 kilojoules in this case. Now, we can also get the frequency factor. So what is this frequency factor? The frequency factor essentially gives you a rough idea of the number of collisions that need to occur in order for a fruitful collision to happen. So a reaction, like again, most of the time the particles collide, they bounce off each other. Gives you an idea essentially of the molecular orientation factor in this. So this is very easy to get. So the y-intercept is equal to the natural log of the frequency factor. So the natural log of the frequency factor equals 26.8. We could do e to that, and we're going to get a huge number. So e to the 26.8 is going to be a big number. We get 4.4 times 10 to the 11th, or 4.36 times 10 to the 11th. Don't really worry about too much about what the frequency factor means, but now you can solve for it. The activation energy is far more important. Come on. So you can see that's exactly what we just got. We got the 93,100 joules per mole, or 93.1 kilojoules per mole, and we got that frequency factor right there. Now, here's the crazy thing. We chemists are super duper lazy. Tomorrow in lab, you will do this. You'll do it for 4 different temperatures, and we will make a line of best fit tomorrow in lab with 4 data points, right? So we're going to have 4 data points. We'll find the line of best fit. Okay, but we chemists are super duper lazy, and we usually are even lazier than we're going to be in the lab tomorrow. Okay, the minimum number of points you need to make a line is 2, right? So the minimum number of trials that you would need to get an activation energy, okay, would be 2 different temperatures, okay? Because think about it. If I have 2 different temperatures and I do them really well, I should be able to make a line, right? Okay, using an Arrhenius plot. Not great science. Obviously, the more data points you have, the better, right? That's usually like the moral of science, right? More trials is better than less trials. But if you're in a pinch and you want to get that activation energy, the minimum number of data points you would need for an Arrhenius plot is 2. And if you only have 2 points, you don't even have to make an Arrhenius plot. You can use what's called the 2-point Arrhenius equation. So the 2-point Arrhenius equation is kind of crazy. You're going to want to put this on your formula sheet. I'm going to show you how to use it here in a second. We're going to talk about it. There's 2 ways to write the 2-point Arrhenius equation. I personally like to do it this way. In the homework packet, they do give you the other variety. Dr. Weinstock Collins, who made the homework packet, he likes the other way to write it, but either equation going to give you the right thing. So the 2-point Arrhenius equation says the natural log of the rate constant at the second temperature divided by the rate constant at the first temperature is equal to positive activation energy over R times 1 over the first temperature, got to be in Kelvin, minus 1 over the second temperature. Now, doesn't matter how many times I say this, somebody's still going to send me an email or yell at me. Listen, in the homework packet for this, Dr. Weinstock-Collins puts a negative here, and then that switches the temperatures. So it's the exact same equation, right? It doesn't matter. It doesn't matter. I like to do it here because I don't like to have that negative out in front, but whatever, man. Y'all do you. Notice that this rate constant goes with this temperature, and this rate constant goes with this temperature. Okay, you got to be really, really careful when you use this formula. Okay, let's try one of these 2-point problems. The nice thing about the 2-point Arrhenius equation is that you only have to do 2 trials at 2 different temperatures, and you don't have to make a crazy graph. You can just go right into an equation. Is it better than the graph? I personally don't think so, but is it easier? Oh my goodness, yes. Way less time, and it's easier. So we got a reaction here between nitrogen dioxide and carbon monoxide. We're making nitrous oxide and carbon dioxide. That's a pretty crazy reaction. We have the temperature and the rate constant. So somebody ran this at 701 Kelvin. They got 2.57 molar in the negative first times seconds to the negative first for the rate constant. This must be a second order reaction. Not that it matters, but look at the units of the rate constant. It must be second order. And then they ran it at 895. They got 567, and they want to know what the activation energy is. So if you give me a second, I'm going to copy this information down onto the board. All right. This is mostly plug and chug and staying organized. So we're going to plug the rate constants into the correct spot. We're going to plug the temperatures into the correct spot. We're going to plug in R, 8.314, and we're going to solve for EA. So we got to be super organized. So here we go. This is going to be the natural log of the second rate constant, 567, over the first rate constant, 2.57. That's going to equal the activation energy over 8.314 joules per mole times Kelvin, times 1 over the first temperature, 701 Kelvin, minus 1 over the second temperature, 895 Kelvin. Now, first thing, the Kelvin cancels out. We're going to be left with answers. We're going to be left with an answer in joules per mole. We'll get there. Here we go. First thing, let's get that left side of the equal sign. We get 5.40 equals EA over 8.314 joules per mole times, let's get that, 1 divided by 701 minus the quantity 1 divided by 895. That's going to be 3.09 times 10 to the negative fourth. Now you got options here. You can multiply by 8.314 and then divide by 3.094 times 10 to the negative fourth, or you could do that. So that's going to be EA times, let's do that, divided by 8.314. That's going to be 3.72 times 10 to the negative fifth moles per joule. Then we're going to divide by 3.72 times 10 to the negative fifth moles per joule. And if you're keeping track of the units, moles is in the denominator, joules goes to the numerator. We're going to get joules per mole as our units here. And we're going to get a 3 sig figs. Let's do 145,000 joules per mole. Usually we give activation energy in kilojoules, divide that by 1,000. The activation energy be 145 kilojoules per mole for that reaction. So the 2-point Arrhenius equation, the math's not that crazy. You just got to be super organized. You got to make sure that those match up, and you got to make sure that those match up.